things to finish before putting in the transistor. So here is the summary, right? So we have derived the three important equations for you to learn p-n junction or a diode, right? You need the equation to evaluate the turn-on voltage or the contact potential. That's the first equation. Second equation, you need to know what's the width of the depletion region, right? So that is especially important for optical devices like a solar cell or photodetector because of the useful currents excited by the sunlight of the photons is from the depletion region. You only have the electrical field inside the depletion region, right? So you need to know what's the width of the depletion region. And then after the p-n junction is turned on by a forward bias or turned off by the reverse bias, you need to know the relationship between current and the voltage, which is the diode equation. So these are the three equations. I bet most of you have learned the origin of these equations. But again, please keep in mind, never forget the assumptions we made during the derivation of the three equations, right? So these are the four assumptions. We need to review them again quickly. What is the first assumption? Number one, we have a no voltage drop in the CNR. What is CNR? CNR 是什么？CNR. Come on. Yes. Charge neutral region. What do we mean? Charge neutral region. When we say charge neutral, that means we have equal numbers of positive charge and a negative charge. So the sum is 0. Okay? That means if you have applied a 5 volts bias to the diode p-n junction, all of the 5 volts will be happening in the depletion region. No voltage drop outside the depletion region, which is the CNR, right? So that's the assumption. Remember, that's not always the reality. I will show you what happens if this assumption is broken. Second one, you have a sharp interface at the CNR and the depletion region, which is easy to understand because when you are talking about a specific number for the depletion region, that means you have a sharp interface. Otherwise, you have no way to use one number describing the width of the depletion. Okay? Third one, what is that? What is PP? P is positive, right? Which means the whole concentration in the P region. P is the whole concentration in the P region. So we call it majority carrier, right? 主要载子就是 P type 里面的电动。And again, this is the negative, which means the negative carrier in the n-type region, which is electrons. So we have two major carriers, PP or Pn. Okay? So this assumption is telling you at the edge of the P-type region, which is before the electron going to the depletion region. Here, depletion region, P-type region, interface is here. At this position, very important, this position, the majority carrier is the same as the injected carrier. So this is P of minus XP0. What is this? This is the hole injected by the forward bias. You know the definition of a forward bias, right? Which means the hole are injected from the battery, from the anode of the battery. So this is the equivalent circuit of a bias p-n junction. You have a battery, you have a p-n junction, right? And you have a wire. So this is the battery. For example, you have 5 volts, and this is the terminal, positive, negative. This is x minus. This is x equal 0. This is x equal minus xp0. This is plus xn0. That's the interface between the emission region and the P region, right? So this is the current flow direction, right? So here we have the P at minus xp0, right? That's the hole injected from the anode 正极 of the battery out the forward bias, right? So the third assumption, 第三个假设 is telling you if your bias is not too high, moderate bias 就是 moderate 就是适当的，不要爆冲的，爆冲的就不是我们讨论的范围。适当的 which what do we mean by moderate? Moderate is telling you all of the injected sorry. I say something wrong. Please make a change. This is delta. Okay? So the hole injected by the forward bias is the difference we make. Okay? So the third assumption is that this is what I want to say, okay? That means this guy, the change due to the forward bias is very small, which means delta P at the boundary is much less than PD. Right? That's the key of the third assumption. Delta means the change or the difference before and after the bias. That's the additional hole increased by the bias. Okay? Delta 就是一个差异嘛，对不对？你在正偏压所产生的差异，对 PP 来讲怎样？可以忽略不计，因为 PP 实在太大。Okay, because PP is so large, if you add more hole concentration from the battery, you can still assume the change due to the bias is nothing compared to the original concentration in the P-type region, right? Because the majority carrier is so high, I can give you an example, let you feel the difference. For example, usually PP is on the order of, give the example. PP we 10 to the 18 Cn minus 3, and the delta P at the minus xp0 can be 10 to the 12. Although it is a huge number, but it is still 1 million less than the PP. So if you add these two together, 10 to the 18, 10 to the 12, you can ignore because this is nothing compared to PP. Understand? That's not how. So this is the definition of moderate bias or moderate injection. That means the injected carrier is much less than the majority carrier. Okay, that's the third assumption we made. Okay, just to remind you, your bias cannot be too high, otherwise the third equation is no longer valid. Okay, these three equations is only valid with all of the four assumptions. If these assumptions, any one of them is broken, the three equations are not correct. Okay? So that's the third equation. No, third assumption, which means you have a moderate injection, meaning the injected electrons or injected holes, because electrons is injected from the N region and the holes are injected from the P region, right? So here, again, I also say N is equal to N at xn0, right? Because when you have injected electrons from the cathode of the battery, these injected electrons is nothing compared to the majority carrier in the region. Okay? I will show you what happens if this assumption is broken. Okay, but make sure you understand the importance of this assumption before I tell you the reality. Okay? Hope you understand. 可以理解吗？第三个假设其实还蛮重要的，等一下告诉大家。第三个假设不成立的时候会发生什么结果 ？How about the fourth one? That's super famous. So you can have a special name, which is called Shockley ideal approximation. Shockley is the name of a scientist, right? What did he say? He said the recombination in the diffusion region can be ignored, which means when electrons go into the diffusion region, it will not be recombined by the holes. Why? I give you an example, right? How can you assume there is no recombination between electrons and holes in the diffusion region? Why? 为什么我可以假设电子跟电动在空法圈里面不会复合？这个假设超重要，对不对？所以它有一个名字叫做 Shockley ideal approximation。啊 ？Anybody remember? Why can we have the fourth assumption, assuming zero recombination, which is not intuitive, right? Electrons and holes are supposed to recombine with each other. How come they cannot do it?陈九如，我们来。为什么电子跟电动在空法圈里面不会复合？不是啊，一个带正电，一个带负电，应该要互相吸引，结合在一起嘛，对不对？ 可是它在共法区就不会干这种事。Why? Do you know why? Because it takes time to meet each other. And the time for the electron and the hole to stay within the diffusion region is so short. Right? I give you the difference between the diffusion region width and the diffusion length. Right? It takes time. Short answer is because the time for electron and hole staying within the diffusion region is so short. They have no chance to recombine with each other, and then they move out. They move out of the diffusion region, going to the CNR, right? So I give you an example. Let me find it. That's the example, yeah? You see, in a typical doping concentration, your diffusion region width is usually less than 1 micron. In this case, I intentionally decrease the doping concentration to make it longer. You can only achieve only 0.5 micron. That's the wide diffusion region, right? So here I just give you an example. If you make this diffusion region wide by lowering the doping concentration, you can only achieve 0.5 micron, 0.5 micron. However, your diffusion length is 50 micron for electron, 200 micron for hole. What does that mean? What do you mean by the diffusion length of 50 micron? 我们上个就是前2周或是考试前有讲过嘛，对不对？什么叫做扩散长度 ？That's the hole concentration. Did you see the blue line? Right? So the diffusion length is the length here describing the distance of the hole concentration decrease to how much? To 1 over 2.7. You see? That's the physical meaning of a diffusion length. L is in the denominator form of the exponential term, right? So if your diffusion distance is the same as the diffusion length, which means xn in the exponential term is equal to L, what happens? Your hole concentration is decreased down to this red dash line point, make it 10e exponential to the -1， 就是1的负1次方，多少？2.71828倍，对不对 ？What does that mean? That means if the electron and the hole need to recombine and reduce the hole concentration in the M region, you need to travel at least 1 L. L is the diffusion length in order to see enough recombination, right? So this 50 micron and the 200 micron is telling you how long does the electron and holes have to travel in order to make their concentration go down enough by the recombination, right? If they only travel 0.5 micron, you can assume it's just around here, almost no change of the concentration, right? 这样可以理解吗？你走的距离如果不够长的话，你不会 recombine。距离长就是等于时间长，对不对？你一定要待够久的时间，或是走够长的距离，你才会遇到足够多的电子电动，它们才会结合。假设它需要走200个 micron， 才能让它原来的数量少掉2.7倍，那它只有走0.5个 micron， 你觉得它可以遇到多少个电子或是电动？这样可以理解吗？所以大部分的情况下，the diffusion region is so short compared to the diffusion length, so you can assume zero recombination, which means the electron and the hole concentration does not change at all within the diffusion region due to the recombination. 这样可以理解吗？可以哈。Right? So that's the false assumption. Okay? If you can understand this, we will tell you the reality. This is the figure, very important. Make sure you understand this. The figure I showed you before the midterm. The 4 figures, 2 of them are concentration, 2 of them are currents. Make sure you understand every line in these 4 figures. Why do you need to understand it? Do you know why? Because you will see it again in the final. Okay? Make sure you don't forget it. If you want to forget it, you forget it after the final exam. Otherwise, you will have a trouble. Okay? 对你们够好了吧？对不对？一直泄题，泄不完。Okay. So, in this figure, I show you 2 IV curves. See, there are 2 IV curves. Maybe I can draw it again. V, I, right? So, ideally, what do we mean by ideally? Ideally means you have the 4 assumption, which is the situation for ideal. Okay? Ideal situation, which means you have the assumption not broken. Okay? Ideally, your IV curve is the green line. That's the ideal IV curve. Ideal IV. Okay? I equals to I0 times exponential term kd uv minus 1. Right? But you will never see this ideal green line in the reality in your measurement. Never. Impossible. Why? Because what you see is always like this. Smaller. That's the real one. How do you show the difference between ideal situation and the real situation? You have one more constant in the real IV curve. Here, N in the denominator of the exponential term is the identity factor. 理想因子。Now you know why n is put in the denominator of exponential term, right? In ideal case, we can say, oh, this line is very steep because you have the n factor equals 1, right? But in reality, you will never see this ideal IV curve. No way. What you see is usually something like this. N equals maybe 1.8, which means the bias you apply to the diodes is used up by 1.84 decrease, right? 它被除以1.8倍，本来是5伏的偏压，除到1.8，剩下多少？你除以1.8，剩下3点多， right? If you divided the voltage, for example, 5 volts by 1.8, you have only around 3 volts. You lost 1 point something volts because of the reality issues. Okay, which means the voltage drop in the PN junction. Okay, so this is R representing the resistance of the PN junction, right? Okay, 5 volts, for example, 5 volts. Okay, you have some factor make this 5 divided by 1.8. Okay, I'm sorry, 5 volts. Making your current lower than the ideal one. 5 volts, suppose this is 5 volts, supposed to give you this much current, right? But in reality, you have only here, right? So this is ideal. This is real, right? Ideal and the real. What happened? Why did you lose some of the bias applied to the PN junction? Something wrong. Otherwise, you're supposed to have a higher current, right? So here is the issues. See, I show you the IV curve in reality in log scale. Okay, so this is a linear scale. And what you see in the slides is in log scale for the currents. Okay, so it's a little bit different, but it is the same thing to plot the IV curve. You just change the figure from linear scale to log scale, right? So you can see in the low voltage, what do we mean by low voltage? Low voltage here, we are talking about the voltage below 0.3 volts. 0.3 volts, 0.3 0.3伏。好，我们叫它是小的偏压。And you see what is the N at 0.3 volts or less. The identity factor below 4.3 volts is 2, which means your voltage is lost by half. And because you need to divide the voltage here by 2, making 5 become 2.5. Why? Because in this region, you are breaking the false assumption. One of the assumptions is broken. at the low voltage bias. Right? The false assumption is what we just emphasized. We assume there is no recombination inside the depletion region. However, this is not the case. Especially when you have a small bias in the forward direction. Right? Actually, the IV curve is only ideal in the middle range of the bias, where you can see n equals 1, which means this region you have an ideal case for the IV curve. If the voltage is too low or too high, you don't follow the ideal situation. For the low voltage, your depletion region actually is wider compared to the depletion region in the high voltage. Right? So in this case, you will have more or less recombination between electrons and holes compared to the situation in the high bias. High bias means the bias above 0.3 volts. Right? So you know this depletion region will become smaller, right? Smaller. Enter high VF. Larger. Enter low VF. Right? So when your bias is small, your depletion region W is longer, which will give you more chance to see electron and hole recombine in this larger depletion region. Right? So it's not 100% true for the false assumption, especially when you have a low bias. Because at low bias, this depletion region is wider. If you increase the bias higher, you can reduce the depletion region because you are applying the electrical field opposite the internal field, right? Internal field is in this direction. But the bias field is in this direction. Right, so they are in the opposite direction. This yellow E0， 黄色的E0，指的就是没有加任何平压的电场 ，internal electrical field without bias. This green EF is the electrical field due to the forward bias, where you have a positive connected to here, negative terminal connected to here. So you can see the electrical field is in the direction from the positive terminal to the negative terminal, in the opposite direction of the internal electrical field due to the space charge, right? So this is the thermal equilibrium, where you have a zero bias equilibrium. VF equals 0, right? And this green EF is due to VF larger than 0. When you have the bias in the forward direction, you are making the internal total electrical field smaller because you have another second electrical field in the opposite direction. So the sum of the two will become smaller than the original one, right? This will make the width smaller at high voltage. So you break the false assumption at a low voltage, and you keep increasing the bias in the forward direction. You will go through the ideal section. You will go to the ideal region, making the identity factor become 1, which is good. When you see n equals 1, that means all of the 4 assumptions are good, no broken. But if you keep increasing the bias, you see the n become larger again. You will see the n become even larger than 2 if the bias is too high. Why? Because when your bias is too high, you broke the first assumption, although you didn't broke the first assumption. Okay? So at the high bias, the first assumption, as I indicated there, is not true anymore. What is the first assumption? First assumption is telling you have a 0 voltage drop in the neutral region, right? That's the neutral region. That's the neutral region. So the first assumption is to tell you no voltage drop, no voltage drop, right? Which is not true at high bias. Right? So if your bias is very high, which means you are injecting high current density through the field junction at high bias. When your current is very high, you will have finite voltage drop outside the division region. So the equivalent circuit will become like this. We have 2 additional resistors. What here? What here? This is the n-region resistance. This is the p-region resistance. And this is the original division region resistance, which is larger, right? Okay. So you know this is the V, and at the low bias, you have a voltage here, voltage drop here, voltage drop here, P, right? So this IV curve with high bias and n equals 2 is that delta P, delta Vp, and delta Vn is no longer 0 at large V. V is here, okay? But delta Vp and delta Vn is equal or close to 0 at small v. I hope you can understand this, which is not difficult, right? You know, you always have a finite resistance. But in order to have a finite voltage drop, you need to know what's the current value, right? Because you know the voltage drop is equal to I times R, right? Current times resistance. If your R is small, which is the case here, and your I is also small, then your delta V is small, which is the case at a low bias, right? But when your bias is high enough, you increase the currents flowing through the P junction, right? Large V means large I, right? So this is current due to the bias. If you make the voltage large, you make the current large also. So the voltage drop when the current running through the resistance in the CNR, N region and P region, you will eventually have a non-zero voltage drop in the P region and the N region. And then, if this happens, the first assumption is no longer true. It's broken, right? Because you see the first assumption is saying no voltage drop in the CNR, right? Which means delta V is 0 here. Delta V is also 0 here, right? This assumption is not true. When your I is very large, even your I is small, but the large current times small I is also give you some finite voltage of delta V. So this is the consideration you should have when your bias applied to the P junction is high, which will make the current lower than you expect. Because in this case, when you have a finite drop in the CNR, you will have less levels. Because the total resistance is not only the R in the equation region, it's also here.能知道好 ，OK。So you have two regions where you have broken the assumption. One region is smaller bias, one region is large bias. Okay? And now we look at the reverse bias, which is the case with V becomes less than 0. You also have a non-ideal results, which is the blue line. Yeah, the dashed line is the ideal case where you have a very small reverse bias. But in reality, your reverse current is larger than you expect. Why? Because we have the generation currents. Something like average breakdown, but not exactly the same. Okay? So here we want to tell you the origin of this generation current on the reverse bias. So this is the lambda we're going to use to explain the generation current, where you can see in reality, your semiconductor is not perfect. What do you mean? That means you will have more or less impurities inside the semiconductor, which will give you additional energy levels between EC and EV. So these additional impurity levels is the real energy level, right? So for most of the case, the current is very small due to the impurity. The current due to the impurity is very small because you know usually the impurity is between the conduction band and the valence band, which means it will take some energy for electrons in impurity level be excited to the conduction band to make some useful current or measurable currents. But if you apply the bias in the negative direction, you can see the deviation between the dashed line and the solid line is become larger and larger. See, the difference between dashed line and the solid line is become larger and larger as you increase the bias negatively. If you increase the reverse bias, you are making this slope steeper and make the width of the division region longer, creating a long division region which will make it more likely for the electron in the impure level to be excited due to the impact ionization, which is the same mechanism for the avalanche breakdown. But it is not as strong as the avalanche breakdown. Because avalanche breakdown is the impact ionization of electrons from the valence band. But this generation current is due to the impact ionization from the electron in the impurity level. That's different. What's the difference? You know? 所以我们现在看到这个在负偏压的实线跟曲线，不是雪崩效应。雪崩效应是不可回复的。Avalanche breakdown is not reversible. Once it happens, it will never come back because you totally destroy the diode. It will not come back again. But if you are only in the generation current at moderate reverse bias, this is reversible. You can also use the PN junction again, as long as you don't enter the avalanche breakdown. So you know the difference between avalanche breakdown and the generation currents. Because avalanche breakdown is from the excitation of electrons in the conduction band. But the generation current, here you see the blue line before avalanche, is from the electron in the impurity level, not the valence band. That's a big difference. Do you know the big difference? What is the difference between impurity level and the valence band? Anybody can tell me? 掺杂所产生的能带跟价电带有什么差异？这个叫做 impurity level， 就是ER，OK，EV 就是 valence band， 对不对？两个都叫做能带，可是产生的这个电流，一个比较小，impurity level 的电流比较小 ，valence band 产生的电流很大，所以一旦它发生的时候就不可逆，因为救不回来，电流太大就把它烧掉。So the key difference between the impurity level and the valence band is density of state. Density of state. Did you still remember the definition of density of a state? 能阶密度差很多。能阶密度就是电子可以出现的能阶。换句话说，价电带可以贡献的电子，或是可以装的电子超级多，它可能可以装100亿个电子。可是掺杂所产生的能带能阶密度远低于价电带，它可能产生100万个。One is 1 million, one is 100 million. So much difference. So the current from the impurity level and the current from the valence band are so much different. Electrons excited from the valence band is much larger. Concentration is much higher than the electrons from the impurity level because of the huge difference in density of states. 所以这个产生的电子远少于价电带产生的电子，因为能阶密度差太多了。价电带的电子密度超高的，它的能阶密度超高，所以价电带产生的电子很多，所以一旦它被激发出来，那个电流超级大，大到整个把电晶体烧掉。可是如果是 impurity 掺杂所产生的能带，它的能阶密度远小于价电带，所以它产生的电子就很小。电流当然就比较小，就比较不会把这个元件烧掉。OK， 所以它是一个可逆的反应，只要它不要发生雪崩效应，都还是可以用。雪崩效应一旦产生之后，你的二极体就冒烟，那就要换壳了。Okay, let's take a break.
是这个东粉它是谁？
谢谢。